We are on to our second practice exam, which is question 1. Actually, and question 1, we're going to be vacuum forming trash bags. So trash bags are typically made of polyethylene. They undergo this process, which is extremely interesting. So they basically vacuum form these trash bags. So you basically, you pull it over a mold, a vacuum forms, and you can kind of see the process that's going on here. So you produce that molded sheet, you lift it off the mold, and then you're good to go. So in this problem, my mold is going to be really, really simple. It's just going to be a square mold, and I'm only interested in the top surface. And I want to describe the stress and strain state in this material right here. We can kind of non-dimensionalize this as instead just a block of material like this that's being pressed down here and free at every other ends. Also, the mold is lubricated, no friction between the mold and the material. And the initial thickness of material will be, so our Ti is equal to 0.1 meters. Our final thickness, TF, is going to be 50 micrometers. And we're asked to determine the full stress and strain tensors quantitatively. Draw the 3D Moore circle. What's the rotation? Get a principal stress state. So let's go ahead and tackle this problem one by one. So in this setup, there's no, basically, let's look at our stress tensor first. So there's lubrication on this between the mold and the surface. So with that, I know that my shear stresses here will be 0. I know from equation 66 that my shear stresses are 0. I know then that I also have that my shear strains here are all going to be 0 as well. From this diagram, I definitely know that there's going to be a stress in the 3, 3 direction. And is there any stress in the other direction? Actually, let me draw my coordinate system. 2, 3. Any other stress or stress in any of the other directions? No, because my material is unconstrained. So there's no other stresses. This is a simple uniaxial stress problem. But however, there will be a strain in the 1, 1, there'll be a strain in the 2, 2, and there's definitely a strain in the 3, 3. And we know that the strain in the 3, 3 is going to be this initial thickness of 0.1 meters. So it's going to be my final thickness, so 50 micrometer minus 0.1 divided by 0.1. So let's go ahead and start to solve this problem. So 0.1 meters. So my E33, let's go ahead and write this out. E33 is going to be my final thickness is going to be 50 times 10 to the minus 6 minus 0.1 divided by 0.1. That's going to be quite a large value of strain. Yes, very quite large. But again, polymer materials can be at least 1. Could go all the way to 10 values of strain. So that's my strain in the 3, 3 direction. So now I have 3 unknowns. I need to know what's my strain in the 1, 1 and the strain in the 2, 2. So I also know that sig 1, 1 is equal to 0, sig 2, 2 equals sig 1, 1, and sig 3, 3 does exist. So actually, I actually do have 3 unknowns. So let's go ahead and solve for this problem. So I'm going to solve. Also, what is my material? Polyethylene. So I know that if my material is polyethylene, my Young's modulus is going to be 1 gigapascal. Poisson's ratio is 0.4. Let's go ahead and define those values. So y equals 1 times 10 to the 9th. Y equals 1 times 10 to the 9th. Nu is equal to 0.4. So I'm going to go ahead and solve that my strain, for example, let's start in the 1, 1 direction, which is actually not going to be E1, 1 is equal to 1 over y times. I know that my sig 1, 1 is 0. Actually, let's just leave it. Sig 1, 1 minus nu times sig 2, 2 plus sig 3, 3, just to get used to kind of writing it in this manner. And then let's copy and paste. Let's figure out all these other values. And finally, here, we're solving for, we don't need sig 1, 1. We need E1, 1. I need E2, 2. And I need sig 3, 3. So let's go to E2, 2. So I need sig 2, 2, sig 1, 1. Then E3, 3. I'm going to set that. Make sure this is a double equal. Double equal. Make sure this is also double equal. Sig 3, 3 minus nu times and then sig 1, 1. All right. let's solve for those values, and this is what we get. So let's define these here. Get these values here, and let's see if they make sense once we write them up. So the stress is definitely negative, which is good, and the strain in the 1 and the 2 direction is positive, which makes sense because looking at the problem setup, it should be expanding if we compress that material. So everything's looking good, at least qualitatively. We need to draw the full 3D Moore circle for this stress state. So we know that we already, our stress state was already in the principal. So sigma 1, 1, which was equal to 0, 0, and then sigma 3, 3. No 0 there. So this was kind of our stress state. So if we look at the 3D Moore circle, it's going to be just this 0, 0, and then sigma 3, 3. So this is just our Moore circle. What's rotation to get the principal stress state? We're already in there. So 0, maximum shear, 45 degrees. What's our maximum shear value? It's just going to be sigma 3, 3 divided by 2. And that's going to be absolute value. That'll be your maximum yield stress. I'm worried that this material will yield during the process, determine if it will yield via Rankine, Tresca, and von Mises. So Rankine, we know that sigma 1 is greater than sigma y, when Tresca, sigma 1 minus sigma 3 is greater than sigma y. Von Mises, we kind of know that criterion as well. And the yield strength of polyethylene is 25 megapascals. So when we look at these values right here, let's look at our stresses. So technically our sigma 1, our maximum normal stresses, is going to be 0 and 0. So sigma 1 is equal to 0, which is equal to sigma 2, and sigma 3 would be our negative value. Again, going strictly by our definitions, you can see here, this is basically approximately, I'm going to say, minus 1 gigapascal. Let's go ahead and double check that. Yep, I agree with that value. So, but because we're in compression, you can kind of think about that in terms of the yield strength in the kind of compressive mode as well. So let's go ahead and let's think about what this is going to tell us. So if we consider, again, we're kind of compressive, this 1 GPa, so we will definitely yield via this guy. We'll also yield via here, and then our von Mises criterion, we kind of calculate that value out. So let's go ahead and look at our von Mises right here. So I'm going to say my sig 1 equals sig 1, 1, sig 2 equals sig 1, and then my sig 3 is equal to sig 3, 3. So, oops, I'm going to call this sig 1. So if I want to solve this out, square root 1/2 times sig 1, sig 2 squared plus sig 2, sig 3 squared, and then plus sig 3 minus sig 1 squared. And we can see we still get this value, so we're definitely going to yield. We're yielding via everything's yielding. Just like in our last problem. We're always getting these problems where everything yields. Excellent. So me some samples of the trash bags. They found some really interesting and confusing behavior. Here are some of what's the type of yielding that's going on in these pictures, explain, and draw where the stress may have been applied to produce these yielding mechanisms. So we know here this is crazy. And then we know here that this is going to be shear banding. Shear banding. So shear banding, they know that let's say that this angle is approximately 45 degrees. So if that's the case, I pulled here and here. Or I compressed the material here and here. Or I compressed the material here and here. Or pulled it here and here. So lots of different mechanisms that occur here. But for here, crazing, I know that I have to pull normal to this fracture surface, and I have to be in tension. I cannot be in compression. Crazing, I cannot have compression occur and basically form this yielding mechanism. So that actually solves, can these mechanisms occur under compression loading? Yes, for shear banding. So yes, but no for this one. No. So basically we know that if you see this image, we can't have formed it with our other method because we're in compression. We're in full, there's only uniaxial compression going on in this process. So those trash bags can't be formed by vacuum forming. Instead, this must be the kind of yielding that we observe and see, because here compression is allowed in order to kind of form these values. All right, so that's the first problem done. So next time we're going to get into some balloon animals, and yeah, I'll see you all in the next video. Thanks. Bye.